Okay, so next video is going to look at interference, which is another wave phenomenon, and standing waves. So let's get into it. So before we move on to interference, we need to understand what we mean by the term phase, because we'll be using it a bit within this video lecture. So when we're talking about a single wave, we can talk about phase in the single wave. We can talk about points as being in phase with each other if they have the same vertical displacement. So in other words, they're at the same point on the wave. So in the diagram below, we have 5 points, A, B, C, and D. And out of those 5 points, A, B, and D are all in phase with each other because they're all at the top of a crest. And C and E are also in phase with each other because they're sort of halfway up and heading upwards. But A and C or B and E are not in phase with each other because they don't have the same vertical displacement. So not at the same position on the wave. So that's for a single wave. We can also talk about phase when we're comparing two or more waves. So for example here we have two waves, wave 1 in blue and wave 2 in red. And you can see that we say that wave 1 is in phase with wave 2 if they line up with each other. So in other words, the crests of wave 1 matches up with the crests of wave 2, and the same with for the troughs. Or we can say that waves are out of phase with each other if they don't line up, and in fact it's the opposite. So in diagram B here, we can see that the crests of wave 1 lines up with the troughs of wave 2 and vice versa. So we call those waves as being out of phase. Now this is important because we need to use this concept when we start looking at interference. So interference is the phenomenon when you have more than one wave traveling through the same median, meeting at a point. So you can have like two different water waves. So let's say you have a pond and you drop two different rocks into that pond. Each rock will produce water wave ripples, and as those water wave ripples move outwards, they'll meet, and where they meet, they kind of overlap with each other and produce a new wave, and that's what we call wave interference. Or another way we could refer to that, we sometimes call it the superposition of waves. So what we're going to do here, we'll look at a few examples where we have interference between two waves that have the same wavelength and the same frequency, and that's important because if we don't have the same wavelength and same frequency, the maths just becomes too complicated for a year 11 level. So we'll just stick to same wavelength, same frequency. All right, so the first example we're going to look at here is what's called constructive interference, where two waves with the same wavelength meet at a point, and when they meet, they're in phase with each other. So the crests of one wave matches with the crests of another, and the same with the troughs. So if two waves meet and they're in phase, then you'll have what's called constructive interference, where they add together to make one bigger wave with the same wavelength but a larger amplitude, as shown in the diagram here. So that's constructive interference. The second example we can have is what's called destructive interference. Now when you have destructive interference, two waves meet at a point, but in this case the waves are out of phase with each other, so the crest of one wave meets the trough of another, and when that happens, you get a wave with either a reduced amplitude, or if the two waves that meet have equal amplitude, then they'll add up to nothing, zero amplitude, as shown down here where you have that red line. So destructive interference produces a wave that's either smaller, or if the two waves that are meeting have the same amplitude, no wave at all, but only at that point. So we're going to have a look at a quick example here. We're going to keep it simple, we'll keep it in one dimension, and we're going to use sound waves. So in the situation here, you have a man or a woman, let's not be sexist, a man or a woman sat between two speakers, A and B. So in this case, they are 10 meters from speaker A and 5 meters from speaker B. And what's going to happen is the two speakers will play the same frequency of sound. Now, when that sound comes through these speakers, when it leaves the speakers, the sound will be in phase. But when the two sound waves meet at the person's ear, they will no longer be in phase because the sound from speaker A has to travel an extra distance compared to the sound from speaker B. Now we call that extra difference the path difference, or delta S for short. So constructive interference occurs when that path difference, delta S, is equal to a whole number of wavelengths. So in other words, the extra distance that the sound from speaker A has to travel compared to the sound from speaker B is equal to an integer multiple, or a whole number multiple of wavelengths. And they'll produce constructive interference because even though the waves from speaker A have to travel further, they'll still be in phase when they meet with the waves from speaker B at the person's ear. So how do we write that mathematically? Well, you can see the formula down the bottom there describes how constructive interference occurs. So we have delta S, the path difference, equals m times the wavelength lambda, where m is a whole number, so it could be 0. So a path difference of 0 means that the distance between speaker A and speaker B would be equal. That's not the case here. The person is further away from speaker A than they are from speaker B. But you could also have a case where m is equal to 1, 2, 3, 4, 5, 6, 7. You can keep doing that forever. But the important part here is that the path difference is equal to a whole number of wavelengths. And you can see from that there's a number of different wavelengths that will produce constructive interference. It's not just one. On the other hand, destructive interference will occur when the path difference is equal to a whole number of wavelengths plus half a wavelength. You need to have that extra half a wavelength to make sure that when the waves meet at the person's ear, that the waves from speaker A will be half a wavelength out of phase with the waves from speaker B. So in other words, the crests of the sound waves from speaker A are going to meet the troughs of the sound waves from speaker B and produce destructive interference. So the formula for that looks very similar to the formula for constructive interference, but we write it slightly differently. Path difference equals m plus a half times the wavelength, where again, m is a whole number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So again, there's more than one wavelength of sound that will produce destructive interference for this scenario. So let's have a look at the actual maths for this. Well, let's do the constructive interference part first. So the path difference, the extra distance that the sound from speaker A has to travel compared to the sound from speaker B, is equal to the 10-meter distance from A to the person, take the 5-meter difference from speaker B to the person, which gives us a path difference of 5 meters. Or in other words, the sound from speaker A has to travel an extra 5 meters. So what I've done over here in this box is I've taken that equation we had before and rearranged it to make wavelength the subject. So lambda equals path difference, delta S, divided by m, where m can be 0, 1, 2, 3, 4, so on. In this case here, 0 is not possible because that would mean that the person was equally distant from speaker A and speaker B, and that's just not the case. So we're going to start with 1 instead. So our first answer for m equals 1 would be 5, which is the path difference divided by 1, equals 5 meters. So the first wavelength of sound that will give you constructive interference is 5 meters. And then for the second wavelength, m is equal to 2. So we do 5 divided by 2, and that gives us a wavelength of 2.5 meters. That will also cause constructive interference. And then for m equals 3, it's a wavelength of 1.67 meters. For m equals 4, it's 1.25 meters, and so on. If I wanted to work out the wavelength for m equals 5, I'd do a path difference of 5, it's divided by an m value of 5, which would give you another wavelength of 1 meter. So basically, there's an infinite number of wavelengths that give you constructive interference. Now, what does it sound like when you have constructive interference? Well, basically, the person that's sitting there at that point is going to hear a slightly louder sound because there's going to be constructive interference, which is going to increase the amplitude of the sound waves. And how we perceive the amplitude of sound waves is as volume. So we'll hear a louder sound at those points for those particular wavelengths, but only those wavelengths. Now for destructive interference, we're going to use a slightly different formula. We take the formula we had for destructive interference, and again we rearrange it to make the wavelength the subject. So we've got over here lambda, the wavelength, equals the path difference, divided by m plus a half. That half part is important to get destructive interference. And you can see through here, I've done the calculations for m equals 1, m equals 2, m equals 3, and m equals 4. I've just realized as I did it, I left out m equals 0 though, because you can have m equals 0 for destructive interference in this case. That would be 5 divided by 0 plus a half, which would give you 10 meters. So I left out another answer there. 10 meters also gives you destructive interference as well. But each of these wavelengths of sound will produce destructive interference, but only those wavelengths. And what would destructive interference sound like? Well, it's going to sound like basically a quieter sound than what you get normally. You won't get no sound at all because the sound from speaker A has to travel further to get to that person, so it'll be weaker by the time it gets there because sound gets quieter as you get further away from the source. But when those two waves meet, they'll make a slightly quieter sound than what you'd have if you just had a single speaker by itself. So that's destructive interference. Okay, So we're now going to take that idea of constructive and destructive interference and apply it to waves on a string, which is what we call standing waves. So think of it like this. Suppose we have a string or a rope or something like that, and we give that rope a flick to produce a pulse. As shown in this diagram here, that pulse will travel to the right, and it hits the point where the string or rope, whatever it is, has been fixed to the wall. When it hits that point, it'll reflect off the wall and go back in the opposite direction. But when it does that, it'll be inverted, which means it gets turned upside down. You can see the pulse is upwards to start off with, but when it hits the wall, it gets reflected backwards, and now it's upside down. Now what can happen there is if that pulse then meets, that's being reflected, then meets another pulse heading in the opposite direction, those two pulses can interfere with each other and produce either constructive or destructive interference depending on their position on the rope. So what happens then is you get what's called a standing wave. If you can make continual pulses along a string, you'll get a standing wave, which looks a bit like a regular wave, but instead of moving, it just kind of oscillates upwards and downwards on the spot. So to give you an idea of what that looks like, I'm going to get out of this PowerPoint for a minute and go to this little animation here. Okay, so firstly we've got a rope that's been fixed at one end with a clamp. And what we're going to do is just do a quick pulse with that rope, just to illustrate what I said before about how the pulse gets reflected upside down when it hits the fixed end. So if we watch the pulse, you can see as it hits the fixed end, it gets reflected upside down and heads in the opposite direction. All right, so that's just a single pulse. Now, if that single pulse was to happen to meet another pulse heading the opposite direction, you can see you start getting these weird effects happening. So if you keep making pulses and those pulses keep reflecting off the fixed end of the rope and meeting other pulses heading the opposite way, then what you'll get is something like this. Okay, so that's what we call a standing wave. So you can see that that wave is moving upwards and downwards on the spot. It's not moving side to side like a regular sort of slinky wave does. Oop, now it's stuffed up. Okay, and you can see that there are points there that don't seem to move at all, like the one I've got my mouse over now, and then there are other points where it moves a lot. So if we go back to our PowerPoint, the points where the standing wave doesn't appear to move at all, we call those nodes. So at the node, basically the rope or the string, whatever it is, isn't moving, you could pretty much come in there and touch it with your finger and it wouldn't move at all. Whereas at other points, you have a lot of movement, and we call those antinodes. So the points where you have zero vertical displacement, where the rope or the string, whatever it is, doesn't move, they're called nodes. And the point where you have the maximum vertical displacement, they're called antinodes. Now, the number of nodes or antinodes you have on a standing wave depends on the vibration. So it depends on how the frequency with which you vibrate that string. The faster you vibrate the string, the higher the frequency and the more nodes or antinodes you're going to get on your standing wave. Okay, so over here we've got the first three kinds of standing wave you could have on a string or a rope. The first one is very simple, it just goes up and down, a bit like a skipping rope, and we call that the fundamental frequency. But then as you increase your vibration, you'll go from having a single antinode like that to having two antinodes like this. We call that kind of standing wave the first harmonic. If you increase the vibration further still, you'll get to a case where you've got three antinodes that are moving up and down, and that's called the second harmonic. And then, of course, if you go further still, you'll have four antinodes, 5, 6, 7, 8, 9, 10. You could keep going forever in theory. But the point is, as you increase the frequency of vibration, you get more and more of these nodes and antinodes. So the mathematics around that works like this. Suppose we use the symbol F1 to represent the simplest standing wave, that fundamental one we had before. I'll just go back to it for a sec. This guy here, the fundamental frequency, the simplest standing wave. If we call that F1, then we can calculate the frequency, a vibration that gives you that standing wave by doing this. V, which is the speed at which waves travel along that particular rope or string, that will be given to you in the question if you get that in the test, divided by 2L, where L is the length of the rope. So that gives you the frequency of the fundamental. If you want to get the higher harmonics, like the second harmonic, third harmonic, and so on, then you use this equation here. Fn equals n times F1, where n is the harmonic number. So if you were interested in doing the third harmonic, then n would equal 3. So you'd go 3 times f1 to get you the frequency of the third harmonic. And here we've got a quick example of it. It says, find the frequency of the fundamental, the second harmonic, and the third harmonic for a wire of length 30 centimeters if vibrations travel along the wire with a wave speed of 90 meters per second. So in this case here, L is 30 centimeters or 0.30 meters. V is 90 meters per second, and we're trying to find the fundamental frequency. So we go F1 equals V divided by 2L, so 90 divided by 2 times 0.3 equals 150 hertz. F2 equals 2 times F1, which is 300 hertz. And F3 equals 3 times F1, which is 450 hertz. And you could keep doing that forever. It will give you the higher and higher frequencies. So that's enough on that for now. We'll talk a bit more about this and do some actual demonstrations when we come back to class on Monday. But standing waves are actually quite important because they're the fundamental behind how all sorts of stringed instruments work. So when you have a guitar or anything like that, what you're actually producing when you strum it is you're producing a standing wave along the length of the string, which vibrates and produces sound. So it's actually quite important to music, these concepts of standing waves and harmonics and stuff like that. All right, so in terms of what you can do for me between now and Monday, on page 193 to 196 in your textbook, it's called Mechanical Waves. I'd like you to have a go at 1, 2, 3, 5, 6, 7, and 8. Skip the other ones, please, and I will see you guys on Monday.